For 12A magnetic fields, you need to know, first and foremost, what is a magnetic field. We've done that for electric and gravitation. Magnetic fields are slightly different. They have some similarities, but there's definitely some differences in magnetic fields as well. You need to be able to draw the field of a magnet, if it's a bar magnet, for example, or another shaped magnet. You also need to know what the magnetic materials are. So what are the different magnetic materials that experience the magnetic force? We've got permanent and non-permanent magnets. We've got the Earth's magnetic field, which we'll discuss as well in a second, and then simply what we can do and what we can use in order to determine the shape of a magnetic field and its direction. So first and foremost, this is a very simple magnet, one of the most common magnets that most people have seen since they were in primary school, and it's called a bar magnet. So in your bar magnet, you have what we call a north and a south, basically equivalent to the positive and negative charges, but it isn't a charge. We've called it north and south because they are opposite, and at each end of a magnet, the field lines will go out of one end and they'll come in the other. So unlike a positive charge, you can have just a single charge with its own field, so just a proton and its field, or just an electron and its field. You have to have, in magnetism, a north and a south. So far in physics, we have not discovered how you can just have one pole, which is called a monopole, on its own. For example, if I were to slice this magnet in half, I've got north on this side, south on this side. If I chop it in half, I'm not left with just the north pole and just the south. I have two new magnets with their own north and south and their own north and south again. Okay, so in magnetism and magnetic fields, you have to have the north and the south. The field goes out of the north and into the south. So as you can see, the shape on this one is a very, very different shape to any of the fields we've seen so far. It's not radial and it's not uniform. The field lines, as you can see, are closer together at the very ends of the magnet, and they're further apart as you go towards the sides and further away. What that suggests is the strength of the magnetic field of a bar magnet is strongest at its poles, both sides, and weakest around the edges, and the further away you go, of course, the weaker it gets again. Alright, the field lines, as you can see on a magnet, they leave the north, so the arrows are out of the north, which is always the case for magnetism. It's always out of the north, and it's always back in at the south, and they loop around. So it actually starts, it comes out of the magnet itself and it goes back into the magnet. So it is a joined field line. So it comes out of the north and goes into the south. As you can see, you've got these loops around the edges, and the further away you go, the weaker those loops become. There are still some loops going all the way around. Even though this one has stopped being drawn here and it started back there, it doesn't mean that it's actually vanished and there's no field. It's just that it's so big you wouldn't keep drawing them. Alright, so we kind of stop. The further out we go, we stop drawing them and we draw them coming back in. But technically that field loop should go all the way around. Alright, and just to make a note on this bar magnet would be a permanent magnet, which means it is constantly magnetized. So no matter where it is or what's happened over time, it will be a magnet. And the shape of this magnetic field, which is common for a bar magnet, is very similar to that of the Earth's magnetic field as well. So that's something that we're going to look at shortly. So first of all, you have how do the magnets interact with one another. So for example, positive and negative attract, positive and positive repel. Is it a similar thing for magnets? So if we put a north pole close to another north pole, I don't want the field interaction. I'm not interested at this point how the field lines join together or deflect. I just want to know what the force interaction is between them. And for north and north, just like a positive and positive, they will repel. So the same poles repel, which means obviously when we get to the bottom, north and south, those two magnets will attract. And if you look at these arrows, they are in opposite directions to one another, and they are the same size. And it's not coincidence. According to Newton's third law, if there is a force applied on magnet A by magnet B, then there is a force applied on magnet B by magnet A. Okay, so each force is the same size but in opposite directions. So if it's repulsive, it's outwards, and if it's attractive, it's inwards. So north, north, south, south, repel, and north and south attract. If we then move to what would the field interaction look like, not the force, but the field interaction, just similar to we did in chapter 11c, electric fields. If you move a north and north together, you know they'll repel. What would it look like for the field? It would be that deflection of the fields again. They will not cross. Okay? The south-south, same deflection again. There's actually a mistake in here which was supposed to be there to catch people out, which I'll discuss in a second. And then the north-south, because we know they attract, they again will join, the field lines will join together and they'll cross over, and that's your attraction from north to south. The mistake, as it says here, as you can see, these arrows on the south magnets are actually going outwards, when we've just said that all magnetic fields go out of the north and into the south. So they should be backwards going into the south, not out. Okay. Finally, again, we have a uniform magnetic field. The one we just saw was not a radial field. Okay, didn't have field lines coming along the radius and moving outwards. It was a bar magnet field, a very specific shape. But uniform magnetic fields do exist, and it's exactly the same. If you have a parallel magnet north and a parallel magnet south on this side, or the north is on the inside here and the south of this one is on the inside here, then you will again get those uniform parallel lines between the two magnets, and that just means that the strength of the magnetic field between those two separate magnets is the same strength everywhere. All right, it's the same definition for uniform magnetic fields as it is for uniform electric and uniform gravitational as well. Okay. The magnetic materials then, so what objects are magnetic, or what objects can experience the magnetic force? Just like in gravity, anything with mass has a gravitational field and experiences the gravitational force. In electric fields, anything with charge has an electric field and will experience the electrostatic force. In magnetism, it is specifically the magnetic materials, also known as, which we'll see in a second, ferromagnetic materials. Only ferromagnetic materials such as iron, nickel, cobalt and steel, which is actually an alloy of those metals, so it must include a ferromagnetic material. Those materials can experience the magnetic force. They themselves can be magnetized to have their own magnetic field temporarily, or they will come close to a permanent magnet and then they will experience that magnetic force, so they'd be attracted. So iron, nickel, cobalt and steel we're going for are ferromagnetic or magnetic materials. Okay? Permanent magnets versus non-permanent. So all of those materials we saw, iron, nickel, cobalt, steel, you can have those metals in front of you and they will not attract other magnets, magnetic materials. Okay, they're just neutral objects. They don't have their own magnetic field as it is. They're non-permanent, but they do have the capacity to be magnetized. So if I were to take a permanent magnet, which has to be an alloy or of hard ferromagnetic materials, so two examples are alnico, which is obviously aluminium, nickel and cobalt mixed into one, that would give you a permanent magnet. So if I pick some alnico up from the ground, for example, it will have its own magnetic field. It will be a magnet already. And ferrite as well, which obviously comes from the term Fe for iron. And so ferrite is a majority iron-based material. That's also a permanent magnet. So they do exist, permanent magnets. But if you take a permanent magnet and you move it close to a non-permanent magnet, then what will happen is it will make that non-permanent magnet attract. Just like in electricity, if I took a charged object and I put it near a neutral object, it induced charge in the neutral object which made them stick together. Exactly the same in magnetism. If I take a magnetic material with its own magnetic field and I move it close to a non-permanent magnet, but it is magnetic material, so it's a ferromagnetic material, then it will induce magnetism in that material, such as iron, nickel, cobalt or steel, and it will make it attract. So if you induce magnetism, you take a permanent magnet or something that has been magnetized, move it close to a non-permanent ferromagnetic material such as iron, nickel, cobalt or steel, then it will always attract and stick to that object. Okay, it will induce magnetism in that object temporarily. It won't become a permanent magnet, it will still be a temporary magnet, but it will always attract. So induced magnetism always attracts the material. Perfect example of this is taking a bar magnet north and south, moving it near a pile of paper clips which are made of, let's say, iron or steel. You pick up the paper clips and they will all attract to the magnet. Now if you get a chain of those paper clips, it means that each paper clip has had a magnetic field north and south induced in itself. So one paper clip has a north and south, which means the next paper clip has a north and south, all north and south attracted to the opposite pole. All have been induced with magnetism and therefore all attract. If you then remove those paper clips from the magnet and you spread them out, They will remain magnetized temporarily for a certain amount of time. The one closer to the magnet will obviously remain magnetized for longer because it was stronger, but eventually they will stop being magnets, they will become demagnetized again, and they will just be ferromagnetic, non-magnetic materials. Okay? Finally, for 12A, one more very, very important thing, other than the uses, for example, you've got fridge magnets. Compasses, the most important and the most common use of a magnet is the compass, which was used for navigation all those years ago. But we've got electromagnets, which are used for picking things up, which we can switch on and off. You've got fridge magnets, which are just used for decoration. You've got magnets that are constantly used in electric generators, which we'll see in the end of 12 and start of 13. But the compass is the one we're going to focus on for now. So the use of the magnets as a compass. Now, what we need to know is that the compass needle is a magnetic needle, okay? And the magnetic needle of a compass has a north and a south pole. And if you just walk around with a compass in any room, anywhere on the planet, you will notice that the compass, the magnet on that compass, which is basically it's going to be attached to a pin so it can spin around with no friction. It used to be made actually in water, so again it could spin around in water with no friction. Okay, so it needs to be allowed to move if the magnetic field interacts with it and it experiences the force. If you walk around with a compass in just any room, you will see that the needle moves depending on where you're moving in which direction. That means that some magnetic field is interacting with your compass needle. Now, a compass needle has to be a permanent magnet. It has to have its own north and south. If it was a non-magnetic, non-permanent magnet but a magnetic material, it would always be attracted to something which wouldn't give you the right direction, for example, because you need it to attract towards the north, for example, the south end, and you need the north end to attract towards the south, so you can actually navigate yourself properly. So a compass needle must be a permanent magnet. Now, if you move that magnet around in a room, it's interacting with the Earth's own magnetic field. Now, we believe the Earth has a magnetic field because of the liquid core. It's got an iron core and a liquid core, and there are convection currents occurring in the core, the liquid core of the Earth, which are generating what we believe is the magnetic field. It actually changes as well over time, which makes things quite complicated. But for all intents and purposes, all we need to know is the Earth has a magnetic field. A compass will interact with the Earth's magnetic field. Since this is a permanent magnet and the Earth's magnetic field has a north and a south side, so it has a direction from north to south, then it will tell you specifically the north of the compass needle will point towards the south of the Earth's magnetic field. Now, here's the tricky part. On a compass, you need the north of the compass to tell you where to go north on the planet. You need to navigate your ship with a compass to the north, which is the top of the Earth. But if your compass needle has a north and it says this way, then it has to be pointing to the south pole. Because if the north of the compass goes forwards, it's attracted to south, like we know opposites attract. The north of my compass is attracted to a south magnetic pole, but I need my compass to tell me to go north. So basically what we're saying here is if a compass needle says north and it says that way, it's taking you to the south magnetic pole because it's attracted to the south, but on the planet it's taking you to the top. So basically if we look at the magnetic field of the Earth, very, very similar to a bar magnet, but as you look at these arrows, the top of the Earth here, which we call the North Pole, if I want to go to the North Pole, then I would go to the top of the Earth, North Pole. However, if my compass needle north takes me this way, points north this way, it must be attracted to a south magnetic pole. That means the Earth's south magnetic pole is at the top of the planet and the Earth's north is at the bottom. And that's why the arrows are coming out of the north at the bottom and into the south magnetic pole at the top. But we call North Pole the top of the Earth. It's very, very important that you think, hang on a minute, on a compass, if the north is that way, and the North Pole is that way, how is my north magnet being attracted to a north magnetic? Well, it's not. The North Pole on the compass needle, on the magnet of the compass, the north of the compass needle is taking you to a south magnetic pole on the Earth, which is at the top of our planet. So it's upside down. Okay? And that's essentially what all the things you need to know for 12. Finally, we can use this compass to determine the Earth's magnetic field by moving around. but we can also use the concept of a plotting compass. So take a small compass, and if I gave you an unknown magnetic field, so I gave you a magnet which I didn't say which was north and south, and I didn't say what the shape of the field was going to be, then you can take a compass, so a plotting compass, you can place the compass next to the magnet, and you see the needle line up with the field. So you put it next to the magnet and you wait for the needle to line up. You put the north, for example, facing the magnet. If the north of the compass is facing the magnet, then you found the south pole on the magnet. If you put your compass around the other side, for example, and your north on your compass points away from the magnet, that means your south is facing the magnet, and therefore you found your north pole. So you can use a plotting compass to find out where the north and the south of a magnet are, and then if you put a dot on the north pole of your compass and you move the compass slightly and see that it might change direction or it might keep going, just put the compass south on the dot that you drew, and the compass lines up in a new direction or the same. Then you put a new dot at the north of the compass again. So follow the north on your compass needle, keep putting a dot, move the compass, and then put a new dot. And if the compass moves, it will take you line of the field line. So a plotting compass can be used to find the direction of the magnetic field that you're trying to find and the shape. If it moves, if it goes out, a dot on either side of the compass and keep moving your compass, and it will take you along the field line and you can draw the shape of the field line. Alright, so you'll be able to practice that and as well. Okay?